Hi, I'm Michael Greenberg, and I want to talk to you today about things we can do to improve lives for shell users. So the shell is incredibly powerful. It's the way that you configure and control your computer. It is sort of the expert's control hash. It's so important, in fact, that when someone else decides to control your computer, the thing they use to do that is called shellcode. The shell is synonymous with controlling your computer. The shell is also pervasive, right? It lives on this incredible spectrum of like one-time single command things that maybe even novices paste into their terminals to continuous use by experts, one-off scripts, and like all the way up to important and critical systems infrastructure. You might say, but Michael, the modern world of ops has completely revolutionized how this works. Nobody still uses the shell. And I would just invite you to look inside the various CI and container and VM affordances that you have, and you will see that all of these are, at core, large piles of shell scripts. And that's great, but it's also sometimes a problem. It makes these things hard to work with. Now, I've spent a little bit of time thinking about the shell pretty hard, and I started by thinking about it as a language problem, thinking that, well, what we need to do is better support the language itself, and that'll make the shell better. But I've come to realize that we need to spend a lot of time thinking about the ecosystem that lives beyond the shell, thinking about the world of commands and other interfaces that we use from within the shell. I think this ecosystem is just as important as the shell itself, if not more important. One reason that I think about this is, well, frequently I'll give a talk about my language work, and people will say, well, can you do a static analysis for Bash? Well, I could, but then I would only help users of that version of Bash and above, modulo, backwards compatibility. If I build new tools for the whole ecosystem, or I can improve the whole ecosystem, then I help everybody, not just users of some particular versions of Bash or Zish or what have you. So let me explain this idea in slightly greater detail about what I mean by the ecosystem. So the shell is sort of a team effort, right? At core, you have the shell and its built-ins. But then there's a bunch of tools that you need to really do work. So you have simple transforms, these sort of like very line-oriented, simple textual things, sometimes not even line-oriented. Then you have distinctly line-oriented transforms that work with really just line-oriented data. Then you have the little languages. Maybe grep belongs in this one, I don't know. But all of these are sort of small languages that people choose or not to master, or maybe leave as sort of obscure incantations that are another way to add a lot of power to the shell. And then in the end, the shell also is home to, well, big languages, right? You might even use the shell to compile your programs, but in any case, from the shell, you'll call programs written in any number of languages. Now, if you were to restrict your attention to just the shell and its built-ins, you have a very impoverished language. It's really hard to do a lot of interesting work in just the shell. I would say that the sweet spot is right here. Right? If you can phrase your problem in terms of this set of programs, right, without having to dump into the big or small languages, right? If you can do this, then you have nailed what the shell is good at. And that's going to be easy working in the shell, and you'll have a good time. This is the sweet spot. So what do you have here? What do you have to work with if you're going to work in this sweet spot? Well, the shell environment itself is just strings. So that's pretty tough. Pipes can work with arbitrary data, but variables really only hold strings due to sort of nulls and white space munging. You're pretty stuck there, right? The environment is really just going to be strings. Some shells offer slightly enriched structures like single-dimensional arrays, but we're really talking about strings. So I would say there's really only one data structure in the shell, the file system. That's it. So if you want to work with structured data, what you need to do is you need to map that data to the file system. Now, this is not a new idea. This is a very old idea. So /proc goes back to 1984. It came to Unix in 91. And then like other people have implemented similar things. So like Bash has these pseudo files where you can work with the file descriptors and TCP and UDP. And this is a controversial thing, right? People are upset that Bash is usurping operating system prerogatives, but it's a useful thing. More recently, people have had similar ideas. So Raphael Wimmer has this paper at Salon de Refuses where he talks about this idea. His example is about pictures, and then some of the responses, people sort of sketched out what this might look like. People seem to agree that this is the right way to work. Right? You need to work with files individual complex data structures as file systems, as directory structures if you want to work with them in the shell. So I had this idea independently. I was like, okay, I'm just gonna build it. So I made this tool called FFS, the file system. And what it does is it takes semi-structured data like JSON or YAML or TOML, and it mounts it using userspace file systems, using Fuse, as a directory structure you can work with. So by way of example, the demo video goes into this in more detail, but by way of example, a common thing that people want to do, 1.3 million people maybe want to do, is work with JSON at the command line. Right? Here they are, they're already in the command line. How do I do this? The first response to this question says, don't do this in the command line, you need to use a real parser. You got to do Python or something like that. Respect. The second answer says, all right, YOLO, let's see what happens, right? So here's this grep command. For the example they have, right, this will work okay for the sample data they give, but it won't work correctly in general. So that's a yikes. They know it's a yikes. I guess I'm one of the haters. It's tough but fair. They go on to actually justify their choices, and I think their justifications here are really worth thinking about. To do a really quick analysis, do you want to open up some other program and figure out the right affordances to sort of get everything going? Maybe you have that on the tips of your fingers. Maybe you don't. And then also these other tools, like the tools that the first answer point you to, like use the JSON library in Python, is bog slow. It's really, really slow. So there's other tools you can use, tools like JQ. For example, this JQ query will do exactly what you want. It'll return a list of all the text fields of these tweets. So there's tools that let you do this, but do you know that tool? So my thought is, let's see what happens if you don't have to know that tool. What can we do working in that sweet spot? Let me show you how FFS works. Here's a JSON file. It's got a bunch of important metadata about me. We want to map it into a file system. So you'll start up the process that runs it. You run it in the background. And the -I here means we're going to work in place. So any changes we make to this directory structure is going to get made right back to that JSON file. So this JSON file corresponds to this file structure. This is the output of the tree executable, just showing you the structure here. You can see how some of the lists worked. It all goes there. Now I update it. I write to a file using echo, so a shell built-in even, probably. Could be an executable, probably a built-in. And I write in my Twitter handle, right, and Greenberg. So go there if you want to see pictures of bread and shitposts. When I then unmount, you get this JSON file back. So it's sort of exactly the correct updates put in there. So this is sort of a simple, sort of contrived example. What's a more realistic one? Here I want to find all of the commits in a repo of mine that mention testing. By default, this is only the most 30 recent, but you can get more from GitHub if you want. So I download it, I mount it up, and then I just proceed to write a shell loop. So this took me about a minute. I had to look up in man the exact format for cut. I had to remember it's one-based indexing. But other than that, this basically was a thing that I know how to do as a shell scripter. I tried to figure out how to write this exact thing in JQ. I spent about 5 minutes and gave up. But this just sort of gives me the nice write output. To see how the lists work, so here I have some stuff from Rigveda, and I'm looking for just manual exploration. So like if I don't know exactly what I'm looking for, I can just sort of explore and see what there is if I want to find out more about the data. So this feels particularly nice. This is something that's harder to do with tools like JQ, which are just going to give you the full report. This feels like a nice way to work. Okay, how does it work inside? So the gist of it is you take this JSON data structure, you parse it, and you create this inode table in memory. So this inode table we're then going to use as a model of that tree structure to serve a user system, a file system in user space. So we just serve requests from that structure. The code to do all this is really not that interesting. It's sort of boring work. There's one or two things I want to comment on here. So first, I want to talk about the type. So here, we expose the type of the data that we have recorded in the inode structure using an extended attribute. And what this lets you do is control the output. So notice here, favorite number here, 47, is stored as an actual JavaScript number, as a float. But maybe I want it to be a string. So what the extended attributes let us do is we could overwrite that metadata using some obscure command. And then when we synchronize back, it'll be as the string 47, not the number 47. If you wanted to go the other way, you could do the same by updating the metadata. FFS will try to sort of auto-detect things, but it does a pretty good job overall. Okay, the other thing I want to point out is the way lists get handled. So in JSON and YAML and TOML, there's this notion of just ordered data, like lists or whatever, which don't have names, but every file in a POSIX system needs names. So the default, like we saw in Rigveda, is to just number everything in order. I pad with zeros to get proper sorting. But you're free to just change the name of something. So if I rename hobbies 0 to last, what do we do? Well, when we synchronize back, when we save the inode structure back to JSON, or whatever format, we're just going to sort it using the canonical sort in the locale. So that'll end up just swapping these two, because last will alphabetize after the number 1. So this name is lost when we save it. You're not going to get a perfect match here, but it sort of seems good enough while offering people the right level of leeway. Right? We're not going to forbid any renames or anything like that. There are some challenges here, and I think some are surmountable and some are sort of essential challenges to the domain. So I want to highlight 3 of them: names, like I was just talking about, metadata management, which I was just talking about, and binary data. So some names are just like illegal, right? Like you can't have nulls, you can't have slashes. You're allowed to have a star, but as anyone who's accidentally created a file named star or dash knows, it's not a good idea. You will be displeased. There are other issues too. So in YAML, in the object model, any value can be a key, even like another hash or list. You can't do that in POSIX, so FFS just takes the hash, does something stupid. In TOML, the root has to be an object. It can't be a sequenced thing. It's just a rule for TOML. It's how it works. So these constraints just don't match up exactly. So you get sort of fresh error cases. You get like problems that you could have now that you wouldn't have just working with the data as it is. Metadata handling is kind of tricky, right? Like I use extended attributes. Extended attributes are not a super well-known feature. They're basically just a little bit of metadata you can stick on a file. macOS uses them pretty extensively and has a nice little tool for handling them called Exitor, and it lets you work with them. So if you wanted to create data or whatever, you can use these attributes to change the types of data. And of course, the interface on Linux is different. Get Exitor, set Exitor. There's like no affordance here. Like if you don't know about this, you're never going to find it. Like maybe you'll see it in the man page. This is not a great situation. I haven't been able to come up with good alternatives. The paper talks about some. I don't like any of them. I'm pretty displeased. Lastly, let's talk about binary data. Let's say I put in this super cool and kind of weird picture of me into an FFS file system and I serialize back to JSON. What am I going to do? There's no binary data in there. If you just write bytes, you're going to mess stuff up. So I base64 encode. That's just what I do. Seems like a sensible choice. It's a thing people are really used to. It's a thing that I think experienced developers can quickly identify when they see the output. This feels sort of straightforward. So on save, I can just do base64. If we wanted, we could put like a data URL on the front or something, but I feel no need to do that. You could make it a flag. On load, you might be tempted to detect it and say, "Oh, that looks like base64. Give me the image." But there's a lot of things that look like base64. Like every English word is valid base64. That's kind of how base64 works. So auto-detecting here feels like the wrong choice. What I do is say, look, when I load, it's just going to be, that text. And if someone wants to run a sort of a file system tool, like a CLI tool, to convert base64 to binary, that's their choice. I'm going to trust people to know what to do with their data. You could try to build some auto-detecting logic or something like that, but you're going to get it wrong sometimes. It just feels like the wrong choice. Okay, I want to talk a little bit about performance. It goes fast. It's great. So this is the graph from the paper. You can see here that even on 3 megabyte files, which is sort of on the high end for JSON, it's not really in the noticeable threshold. Like by the time you're starting to type the new command, if you're running the thing in the background, when you're done typing, it's already. So to my mind, this is responsive enough. This is not sort of a super hyper rigorous benchmark. This is just the examples I selected. Since the paper, I implemented lazy loading. So what this says is it says, well, we'll parse the whole structure, but we're not going to build the inode table eagerly. We're going to do it on demand. And this saves you a little bit of time. It saves you time on loading, but also on saving, because any part of the structure you haven't traversed, well, you have the parsed value right there. You don't have to sort of traverse the inode structure to reconstruct the value. So that ends up saving you some time. I think in principle, it's possible to do some form of lazy parsing here to get these numbers up top a little further down. Because of the recursive structure of formats like JSON and YAML and TOML, you can't sort of skip parsing a section, but you can just scan it and save the work of building a sort of an in-memory representation for later. This is trading some space for time, but it's also trading you, some work for double work, right? You'll scan it, which is cheaper than actually parsing it, and then you'll just sort of remember which offsets to go back and look for. Some of the Rust libraries I use already support this, in fact. While talking about these not incredibly detailed performance measurements, it's worth talking about what the right ones are. Right? What are my tasks and languages to make a baseline for evaluating FFS as a tool? You want a mix of reads and writes, you want real-world use cases, but the things you select here matter a lot, and I don't think there's anything approximating even a benchmark suite here. What languages should we compare against for these tasks? Manual use for exploration? Not clear to me how to do that. That sounds like a user study. Using JQ? Coding in Python or Node, coding in Rust, it's maybe a better language apples to apples, right? My Rust code is going to be faster than Python. I don't know the right choices to make here or the right tasks to choose, so I would love input on that. One higher level question I have is the file system and user space approach even the right one? What I wanted to do was take a JSON structure and produce a file system structure that looks like this. This is the gist of what I wanted to do. Fuse is just one way to do it. You could imagine a pair of programs, unpack and pack, that take a JSON file and then unpack it into the appropriate directory structure, and then take a directory structure and pack it back in. Some advantages here would be, well, you could pack anything, right? You could unpack anywhere. It'd be persistent. Maybe you want to leave it there forever. There's some disadvantages. It really uses your storage medium. It really takes up space, wears out your disks if you're doing a lot of it. It's going to be tough to get it to go lazily. But it seems like an interesting alternative to explore. Not clear that file system and user space are even critical here. With that, I want to pull back up a little and take a higher level perspective. Right? All of that was sort of about performance, implementation, lower level stuff. I want to think at a slightly higher level. One of the reviewers pointed out that I am hardly the first person to do this. Right? If you search just the phrase JSON-FS on GitHub, there's 28 matches. So FFS is written really well. They did a really good job. Maybe that will make FFS successful where these, I think, have not been particularly successful. I support more formats. It's well engineered. Maybe this idea fails for some other reason. Maybe it's too hard for people to put into their workflow, or it's too much trouble to get it installed on someone's system, or Fuse is just too high a cost of entry for people to really want to use. So I think there's a real risk here in terms of, will this actually help people in the way they use the shell? That's not clear at all to me. People seem excited about this idea, but also a lot of other people have tried it. Lastly, assuming that it is a good idea, that spending effort to map various formats to POSIX file systems is worth the effort, what other formats would be worth doing? So one that's come up repeatedly in conversations is binary formats. So people who work with binaries like ELF or whatever, or sort of other things associated with binaries like the dwarf format and things like that, have mentioned that it would be useful to have something that let them explore, maybe even rewrite little bits of, using existing tools. So this seems like it could be useful. What other binary formats would be particularly useful? So Raphael Limmer talks about images. Where else should we go with this? XML is another semi-structured format that seems worth thinking about. It's really complicated, particularly PC data. There are already some tools for shell. The XML tooling for that is not horrible. Maybe we should stick with those. Maybe we should give up XML as a relic of the 2010s. And before, I'm not certain what the right approach here is. But I'm very interested to think about what other mappings here to the file system would be useful, because I've come to believe this is the right approach. In any case, thanks for listening. It's been fun being here, and I look forward to talking to you all at PLOS. Thanks.